Okay, welcome to week 12 in review, guys, which is the final week of term 1. It's been a long one. This is the last video to cover our thermochemistry section of SPNT, and we're looking at the 4 ways to calculate the enthalpy for a reaction. Now, we'll assume that it was covered well in week 11 in review last week, the first way, which is to calculate the enthalpy for a reaction from experimental data, so that this is covered. Um, so in this video I'm going to cover using average bond energies, using Hess's law, and then using this formula, which is the enthalpy for a reaction can be calculated by taking the sum of the enthalpy for the formation of the products and subtracting from that the sum of the enthalpy for the formation of reactants. So if we take a look at this worksheet which I gave you guys during lessons, and this was to calculate bond energies, the first thing we need to look at is to calculate the enthalpy for a reaction using bond energies, we must have a definition for bond energy. So the definition for bond energy, if I just write it briefly here, it's the energy which is required. So the energy required to break 1 mole of a particular bond, in a reactant or product which are in the gaseous state. So 2 key points there. It's, well, 3 key points, I suppose. I'll just highlight those. It's energy, so that should be a highlighter, not amazing. So it's energy, and it's talking about breaking 1 mole, and then you're looking at the fact that the reactant or product molecule or atom is going to be in its gaseous state. So that's the key definition for bond energy. The next point we want to raise here is that bond energies values are always going to be positive, and this is because to break a bond, breaking a bond is always an endothermic process. So all these average bond energy values are all going to have a positive delta H. And really they should call them average bond enthalpies, because the units we're using here are kilojoules per mole, which are the units of enthalpy, but they're traditionally known as bond energy values. Part C here, bond energy values given in tables are often called average bond energies. Explain why the listed value of, say, the OH bond needs to be an average value. And this is simply because you need to think about all the different bonds that oxygen, or elements that oxygen can be bonded to. So you can have oxygen bonded to hydrogen, you can have oxygen bonded to chlorine, you can have oxygen bonded to carbon, etc. And then you add up all those energy values, get that number, and then divide it by 3 in this case. So you get the average value, and that's what you use then in the table. And then write a simple equation which can be used to calculate the heats of reaction using bond energy data. So enthalpy for the reaction using bond energy data can be calculated by summing up the bonds broken. So you sum up the total average bond energies for the bonds broken, which will be in your reactants, and then subtract from that the bonds formed, energy of the bonds formed, which would be in your products. So this is products, and then the bonds broken would be in your reactant side. So that's the background theory. The next thing obviously would be to take a look at an example. So if I scroll onto this next page, we have a table of average bond energies here, or bond enthalpies. So all of these values are in kilojoules. Let's get my pen here. Not sure what happened there. Let's go back. So I need my pen. So all these values, these bond energies, are in kilojoules per mole. And remember, they're averaged as well, depending on the possible elements that they can be bonded to. So here's a question. Question 2, calculate the value of enthalpy for the reaction for the following equation or reaction using data from the table above. Assume all reactants and products are in the gaseous state, which is a requirement for calculating enthalpy using bond energies. So the very first thing to do here is to make sure that you take each of these condensed formulae and you expand them out into full structural formulae. So that's what we're going to do. So what we're going to do, as I said, was take these condensed formulae and open them out into full structural formulae. So C2H4 is ethene. So we'll draw that out. Full structural formula, show every single bond because we need to identify the bonds that are being broken and the bonds that are being formed. In Br2, molecular bromine, these two bromines join together like so. And then in your product here, it's 1,2-dibromoethane. So you have 2 carbons in the central chain, and then your hydrogen's coming off, and then your bromines at either end of the molecule. So it's now easier to identify what bonds we have to break and what bonds we have to form. There's 2 ways to do these questions. You can either try to identify which particular bonds are actually broken in the reactants and then which bonds reform in the products. That makes the job a little bit harder when the compounds become a bit more complex and there's a little bit more going on. So what I tend to teach my students, what I do teach my students, is to simply break every single bond on the left hand side and then form every single bond on the right hand side and then just subtract those 2 numbers from each other to get your final answer. Go away. Okay, so that's what we're going to do. We're going to break every single bond on the left hand side and then form every single bond on the right hand side. Okay, so now what we're going to do is we're just going to write out the particular bonds that we have, or the numbers that we have of each one. So we have a carbon-hydrogen bond here. So that's a carbon-hydrogen bond. We have 1, 2, 3 of those. So we put 4 around that bracket. The next type of bond we have on the left-hand side is the carbon-carbon double bond. So we just have 1 of those. And that's that particular compound, ethene, used up. Then we take a look at the bromine. We have 1 of those bromine-bromine bonds. And that's all our bonds on the reactant side. So from that we are subtracting. So we're summing this. And from that we're subtracting the sum of the bonds formed in the product. So we have a carbon-hydrogen bond here. We have, again, 1, 2, 3, 4 of those. 4 of those. Make that a square bracket. We have a carbon-carbon single bond there. Just 1 of those. So we break that, or form that rather. And then we also have 2 of the carbon-bromine bonds. So we put that in there. Now the next thing is we need to go to our table and look up the actual energy values of these bonds. So the CH bond here is, we just find it now, it's 413 kilojoules per mole. So we 413 multiplied by 4 for those bonds. Then the carbon-carbon double bond, we'll locate that here, which is 614 kilojoules per mole. And then the bromine-bromine bond, which is a single bond, is 192. You can see the difference there clearly between the strength of a double bond and a single bond. So that's on the reactant side. On the product side, we have the sum of the following. So the CH bond again was 413 by 4. The carbon-carbon bond here, if we look that up, carbon-carbon bond is 348 kilojoules per mole. And then the carbon-bromine bond, we find that here is 285. And we have 2 of those. So you just have to sum all these up and then subtract them from each other. And if you do that, then the number becomes, so if you do those additions and subtractions up, the enthalpy for this reaction becomes minus 112 kilojoules per mole. And that's how you use bond energies to calculate the enthalpy for the reaction. It's a skill which was actually moved to the level 2 chemistry course last year when it was realigned. So it's essentially on both courses now. Should be straightforward to, as long as you guys basically break every single bond on the left hand side and form every single bond on the right, add up all your numbers and subtract them from each other, you should be fine. The next thing we need to look at is using Hess's law. So if I go back to our original starting point, we now have covered how to calculate the enthalpy for a reaction using bond energies. So we're going to take a look at Hess's law now. Now Hess's law will start off with a nice simple example and then work up to an exam standard question. So let's take a look at Hess's law. And here we go. So with Hess's law, now Hess's law states that if a reaction can be represented as a combination of other reactions, then the enthalpy of the reaction is also a combination or a sum of the other steps. So a combination or sum of the entropies of the other reactions. So in other words, if you had one reaction where you went from reactant A and the product was known as represented by the letter D, the entropy for that reaction, delta or H, would be equal to doing this reaction in individual steps. So if you went from A to B, and then from B to C, and then from C to D, and you add up the entropies for each of those steps, so we call that entropy 1, entropy 2, and enthalpy 3. Hess's law states that the entropy for the reaction from A to D, that energy change per mole, would also be equal to just simply adding up the enthalpy changes for each of the constituent steps there, A to B to C to D. So entropy 1 plus entropy 2 plus entropy 3. So another way of saying this is that the enthalpy change in a reaction is independent of the pathway of the reaction. So would you be asked that in an assessment? Not really, but that's the understanding behind what you're doing with this approach. So here's an example, a simple example for calculating the entropy of a reaction using Hess's law. Now, the question here really is, you're given your main equation, and I'm going to highlight that because what we had during the week was that, and it happens to everybody, is that you have so many equations on your page that your eye starts to get a bit confused as to which one you're focusing on. But this is the main equation. This is the main equation. And the worksheet has been kind enough to put it in bold for you. So this equation would represent that A to D situation. But unfortunately, we don't have the energy or the entropy for the reaction from A to D, but we've been given the entropies for individual steps. So this here could be A to B, this would be B to C, and this would be C to D. And Hess's law says that if we can add up these three individual entropy values for the three reactions that get you to the final product, then you should be able to get the entropy for the reaction from A to D. So that's what we're doing here. Now, we have to take a look at the main equation, and you have to decide what species are reactants and what species are products in the main equation. So we're just going to go through the habit of writing R for reactant beside each reactant species in the main equation, and then P for product. Now the next thing we want to look at is you want to look at the three constituent equations that we've been given. So this is equation 1, 2, and 3. And we want to add up these three equations so that they give this main equation. And then if we can successfully do that, we can just add up the entropy values, and that will give us the entropy for the reaction from A to D. The main question to really ask yourself when you're looking at these in exams is, do you have to reverse an equation? Do you have to reverse an equation? Do you have to multiply by any factor? Or do you have to divide by any factor? These are the questions you need to ask yourself when you're approaching a Hess's law question. So, we look at the first equation here. We have sulfur plus oxygen going to sulfur dioxide. Now in the main equation, sulfur is on the reactant side, and there's no evidence of sulfur dioxide. So the main thing we need to focus on is the sulfur and the oxygen. They are on the right side, so we don't need to reverse any equation here, in which case the entropy for the reaction stays the same. The second reaction, sulfur dioxide plus water goes to plus half oxygen, creates sulfuric acid. Sulfuric acid is a product in the main equation, so it's fine. It can stay there, and you don't need to change anything with the entropy for the reaction. And then in the final reaction, we have hydrogen plus oxygen, half oxygen going to H2O. And again, the oxygen and the hydrogen are on the right sides. So this is a simple example of a Hess's law question. We don't need to reverse anything. In terms of multiplying, you only know that until you see if all the species will add up. So we're going to use some different colors here now. So if we look at our oxygen species initially, we have half an oxygen here, and we have half an oxygen here. These are all on the reactant side, so just keep track of that. The arrows there actually go like that. So we have half oxygen plus another half, that makes 1, and plus that gives you 2. So you have 2 oxygens, which is great, because that's released in the reactants in the main equation. We only have 1 sulfur, so you can put that down as well. Now if we take a look at the water situation here for a second, if a species appears on both sides of the arrow, so as a reactant and product, you can just cancel them out like in an algebraic equation. So there's no water molecules left on either side. And then we want to take a look, and we've used up our oxygen. Should have said that already. So we've used up our oxygen, we just added them all together. The sulfur dioxide will cancel, so I'll use a different color for that. This sulfur dioxide here will cancel with that sulfur dioxide there, in which case all that we're left with now in our equation is the hydrogen from here, and then we go to our products and we have H2SO4. So that successfully adds up to the main equation. So we did no reversing, we didn't have to multiply by any factor, and we didn't have to divide by any factor, in which case these enthalpy values remain unaffected. So you just need to add up those enthalpy values and you get your final answer. So when you add those values up using your calculator, the enthalpy for the reaction, if you were to go from A to D, would be equal to the sum of these individual pathways, which comes out to be minus 1439 kilojoules per mole. And if you look back at the main equation, well, we can't infer whether it was combustion or formation, etc., etc., but the value here is this is the value for the main equation, and that's the correct answer. Over talking the situation. All right, so that's a simple example of Hess's law. We didn't have to reverse any equations, we didn't have to multiply anything, and we didn't have to divide anything. So we're going to have to take a look at a more complex question, and I'm just going to pull up a question here from 2010. So this is the 2010 exam question, which was on Hess's law. Let's see where it is. Here we go. So zinc oxide, it's formed when zinc sulfide is heated in air, and that's your main equation. So we identify our main equation, we put a box around it. That's our main equation. All right. Now in this question, they're not being as generous to us as in the last one. They've given us some enthalpy for formation of different compounds. We've given us the values, but they haven't given us the individual equations for each of the three pathways. So we need to be able to write enthalpy for formation of compound equations. So I'm just going to put them beside each one of these species. Okay, so if we get a different colored pen just for that there. So these individual equations, enthalpy for formation is the enthalpy required, the heat required to form 1 mole of a substance. So the substance in question is zinc sulfide in this first example, so that's the product we're forming. So your arrow faces towards that. You must keep it as 1 mole, in which case we're using 1 mole of zinc plus 1 mole of sulfur atoms to make zinc sulfide. Remember, you're using the elements as they exist at room temperature and pressure. So you'd have zinc metal plus sulfur solid. And the enthalpy for that reaction or formation is minus 200 kilojoules per mole. The next product we're forming is zinc oxide. So we write zinc oxide here. Now, zinc exists as zinc atoms at room temperature and pressure, but oxygen is a diatomic molecule, so we need to use a half a mole there. And then the last product we're looking to form is sulfur dioxide, and that's sulfur plus oxygen. So there are your three constituent equations. And we're trying to add them up to make the main equation. Now remember, we're still considering whether we have to reverse an equation, whether we have to multiply by a factor, or whether we have to divide by a factor. So we need to consider all those things when we're looking at this question. So what we're going to do now is we're going to try and add up our three equations. So the first equation here, equation 1, just call that equation 2, and we call this equation 3. And I get a different color now. In equation 1 here, zinc sulfide should be a reactant, because if you remember, we need to identify reactants in the main equation and our products. And zinc sulfide should be orientated or arranged as if it were a reactant. So we need to reverse this equation. So we rewrite that equation in reverse, and then we have zinc sulfide on the reactant side going to zinc plus sulfur. Alright, now if we do that, then we need to also reverse the sign on our enthalpy for that particular reaction. So instead of it being negative 200, it's now going to be positive 200 kilojoules per mole for that reaction. The next equation, zinc plus a half oxygen going to zinc oxide. And zinc oxide is a product in the main equation, so that's fine. So we'll just write that down as is. Zinc plus a half O2 going to zinc oxide. The enthalpy for the formation of that was equal to minus 348 kilojoules per mole. And the third equation, which is your sulfur plus oxygen going to SO2, that doesn't need to be reversed either, so it's in the correct order, and we'll just rewrite it as it is. And the enthalpy hasn't been affected either, so minus 297 kilojoules per mole. So yes, we had to reverse in this case. Now let's take a look at the situation and see, do we have to multiply anything to make sure we get the final equation? So let's just put our line here. We're trying to sum these three individual equations to see if we can get the main equation. So let's use another color now. So if you look at the zinc sulfide, we need 2 zinc sulfides in the reactants from the main equation, and the only way to get that is to multiply this entire equation by 2. We're going to times this by 2, and 2 zinc, 2 sulfur, and then this has to be times by 2 as well, this enthalpy value. So if we do that, we will now have 2 zinc sulfide on the reactant side. We'll have 2 zincs, and then we will have 2 sulfurs. Now there's no zinc. If you look at the second equation, there's no zinc at all in the main equation. So we also need 2 zinc oxide. So we're going to multiply this as well. So 2 times zinc oxide, and 2 times a half, which will be 1.5, and then 2 zinc oxides. We must also multiply the enthalpy for the reaction by 2 as well, to keep everything even. And now it looks like we may be able to sort out this equation. So just to correct myself, said a silly thing there. So 2 times a half is obviously not 1.5. It's just 1. So the 2 times the half there makes 1. And then you have 2 zinc oxides, and you multiply your enthalpy for the formation by 2. Now the sulfur plus oxygen plus sulfur dioxide, there's also 2 sulfur dioxides in the product, so we're going to have to times this by 2 as well. So you can have 2 sulfur, 2 oxygens, and 2 sulfur dioxides, and multiply the enthalpy for the formation by 2. So yes, we had to multiply. I don't think we have to divide here, because if we look at everything we have now, we have 2 sulfurs, which will cancel with each other here. We have 3 oxygens, if we add those together. We have 2 zinc sulfides. Just keep throwing your eye back up at the main equation to check if you're on the right track. The zincs here will cancel with each other. And then on the product side, you have 2 zinc oxide plus 2 sulfur dioxide, which matches up with the main equation. In which case, we now just need to times all these enthalpy formations by 2 and add everything together, and you get your final answer. So if you add all these together, you get minus 890 kilojoules per mole, which is the enthalpy for the reaction. So that's how you use Hess's law, and I think that's pretty comprehensively covered. Now, just another thing we want to talk about is an alternative way to calculate the enthalpy for a reaction, and this is to use this equation that I said, which was the fourth way. So just scroll down a little bit. So an alternative way to calculate the enthalpy for a reaction, instead of using Hess's law, you can use this equation. The enthalpy for a reaction is equal to the sum of the enthalpy for the formation of products minus the sum of the enthalpy for the formation of reactants. So this process doesn't involve any manipulation of equations. All you need to do is identify the products in the main equation and then the reactants in the main equation, and look at the enthalpy for the formation of each of them and add them up and subtract them from each other. So in order to use this formula here, we're going to just take a look back to our previous question that we did. So we go back here. Now we're using enthalpy for the reaction calculated using the sum of the formation of the energy for the products, minus the sum of the enthalpy for the formation of the reactants. So the product in this main equation was sulfuric acid. The enthalpy for the formation of sulfuric acid can be taken from here. So what we're doing is we're taking 900 minus 900 kilojoules per mole, and from that we're subtracting the enthalpy for the formation of the reactants, and the enthalpy for the reactants were hydrogen, sulfur and oxygen. So the enthalpy for the formation of oxygen and sulfur can be taken by reversing the sign of this equation here. So 297 kilojoules per mole. That covers the energy for the formation of sulfur plus oxygen. This was the enthalpy for the formation of sulfuric acid. And then the only other reactant that we need from the main equation is for the hydrogen, which can be taken from this equation here. So you reverse the sign on that, and you have plus 242 kilojoules per mole. So that's the enthalpy for the formation of hydrogen. And if you add all those numbers together, you get your enthalpy for the reaction, which is minus 1439 kilojoules per mole, which matches up to give you the same answer using Hess's law. Now, a piece of advice with using this equation, I find it a little bit trickier to identify. Go back here. I find it trickier to identify what the what the energy for the products is and what the energy for the reactants is, especially in more complicated questions. So essentially, know how to do both ways, and then you can compare your answer and make sure, well, obviously, if you have the two answers matching, you're on the right track. That is, as far as I can see, my best overview of how to explain how to use Hess's law and that equation there to work out the enthalpy for a reaction. So we've comprehensively covered the four ways for working out the enthalpy for a reaction. And the only other video I need to cover, which is a video on entropy, and I'll do that next, and then that's the entire SB&T course covered with videos. And then we look forward to moving on to our next course.